In this section, we're going to look at using double integrals to find the area of a surface. In Calc 2, we found a special surface area, a surface area of revolution, where you take a surface and rotate it around an axis. And you can use single variable calculus to find that surface area. So here, we're going to compute the area of a surface using double integrals. We can divide the domain D into small rectangles, use the midpoint formula, and come up with it with the surface area. But we have a formula for a surface area. We're going to use this notation, the area of the surface. If you say capital S equals, I will let you, I will be okay with that. So we're going to say capital S or A of S equals, and we're going to do the double integral over the region D, and we have the square root of the partial derivative of with respect to x of xy squared plus the partial derivative with respect to y of xy squared plus 1 is all under the square root. And we take the integral with respect to the area of the region. Now, I'm going to simplify this notation to say the square root of the partial derivative with respect to x squared plus the partial derivative with respect to y squared plus 1 dA. You can also use the notation of partial derivatives and say your partial derivative of f with respect to x squared plus your partial derivative of f with respect to y squared plus 1, all with respect to a. So it's very similar to the area, the surface area that we found in Calc 2. In Calc 2, we said let the arc length formula is the integral from a to b of the square root of 1 plus your derivative of y with respect to x quantity squared with respect to x, and then you put that into the surface area. So it's very similar to what we did there. Don't worry about this. This is not what we're using. And again, I will give you this formula when it comes time for a test, so I won't make you memorize it. And let's look at how to use it then. So this problem says find the surface area part of the surface, z equals x squared plus 2y plus 2, that lies above the triangular region T in the xy plane with vertices 0, 0, 0, 1, and 1t. So if you think about what this is really telling us, we have a triangular region. Let's go ahead and draw it out. So we have the point 0, 0, the point 1, 0, and the point 1, 1. So this is our triangular region that we have here. And so we could say that t is equal to the points x, y, such that x is between, notice the x is between 0 and 1, right here. So x is between 0 and 1, and y is between 0 and, if you look at this, it depends upon what x is. So let's say y is between 0 and x. So 0 to x here. So that makes sense. We want to say 0 to 1, but it's not a rectangle. It's a triangle, so we can't stop there. And we know that z, so let's say z is equal to f of xy, and it's equal to x squared plus 2y plus 2. So when we look back at our surface area formula, we need the partial derivatives. So let's look at the partial derivative with respect to x. So that would be 2x plus 0 plus 0. Let's find our partial derivative with respect to y, and that would just be 2. So then our area of our surface is going to be the double integral over the region. Let's go ahead and space those double integrals accordingly. And I have the square root of 2x quantity squared plus the derivative with respect to y, which is 2 quantity squared, plus 1. And then when you look at your bounds, your y goes from 0 to x. So I'm going to have to do dy first, and then 0 to 1. So we're going to do dx next. So now we get to do the fun of the integral. These could be very hard. My personal philosophy of surface area is you have to be careful as you're doing them, and you have to watch for the patterns that are going to make it work. So here we go. 2x quantity squared. 2 times 2 is 4. X times x is x squared. And then we have plus 4 plus 1. So I'm going to go ahead and say plus 5 because you are smart enough to handle that track with me. And then we have we're going to integrate with respect to y and then with respect to x. So when we integrate with respect to y, all of this stays the same because it is a constant. And we're going to say times y from 0 to x. And so let's bring down the whole integral thing. We have the square root of 4x squared plus 5, parentheses x minus 0, which means x. So let's move that x out front. The integral from 0 to 1, x times the square root of 4x squared plus 5 dx. And I love to integrate. That's why I love Calc 2. So this is very fun. This is a u sub. Let's let u equal 4x squared plus 5. That means du is going to be 8x dx. So dx is 1 over 8x du. So we have the integral and x times the square root of u times 1 over 8x du. And let's change our bounds. When x equals 1, u equals 1 times 4 is 4 plus 5 is 9. When x equals 0, u equals 5. So our bounds are now 5 to 9. And these x's are going to cancel. So we have the integral from 5 to 9 of u to the 1/2 du. I left off the 1/8. So let's put the 1/8 out front. So we have 1/8. And then we have, when we integrate u to the 1/2, we get u to the 3/2. And the reciprocal is 2/3. And the bounds are 5 to 9. So that fraction becomes 1 over 12. And then I have 9 to the 3/2 minus 5 to the 3/2. Now your calculator can do this, or your brain can do it, hopefully. So the square root of 9, the 1/2 power, the square root of 9 is 3. To the 3rd is 27. Minus, let's call this 5 square root of 5. I'm okay with 5 to the 3/2. The Webber sign will not be. So this is our pretty answer here. And then let's look at the picture as to what this looks like. So this is the surface area for the part of the surface x squared plus 2y plus 2, pictured in the blue, that lies above the triangular region T for the triangle below. So what we really found is the surface area of that green surface right there on that curve. This one is from your homework. It says find the area of the surface of the part of the plane 13x plus 2y plus z that lies in the first octant. Now there's a couple things happening here. First of all, you need your function. So we're going to say f of xy is equal to z, which is, let's solve that for z, and I'm going to say 26 minus 13x minus 2y. But also, I need bounds, so I need to look at how that maps to the xy plane. So let's look at the xy plane and what's happening here. So when we look at the xy plane, that means we take the z out. We have 13x plus 2y equals 26. Now, when you look at that on the xy plane, the x-intercept is 2, put 0 for y, and the y-intercept is 13, put 0 for x. So we have this triangular region here, and this is going to give us our bounds. So our bounds are going to be, for x, our bounds are going to be 0 to 2, and for y, we're going to go 0 to that line. So let's solve this line for y. 2y equals negative 13x plus 26. So y equals negative 13 over 2x plus 13. So we could say that this triangular region underneath of it, we're going to call it D, because they call it D in the next part. The points x, y, such that x is between 0 and 2, and y is between 0 and that line, negative 13 over 2x plus 13. So that's our region that we have here. Now, we're going to use that for our bounds for our surface area here. And then we're going to come back up and find the partials. So let's say the partial derivative with respect to x will be negative 13. And the partial derivative with respect to y will be negative 2. So let's go ahead and say the area of the surface is equal to the double integral over the region D. And we have the square root of the partial with respect to x squared plus the partial with respect to y squared plus 1. And we're doing that with respect to the area of the region, dA. Now, the more you write the formula, the more you're going to remember it. But remember, I'm not going to make you memorize that. I will give it to you. And when we look at this homework problem has two parts. So I'm going to finish the surface area and then come back and answer the questions in the homework. So it says the area of the surface is equal to the double integral. I'm going to leave spaces here. And our partial with respect to x is negative 13 quantity squared, plus the partial with respect to y. Partial derivative with respect to y is negative 2 quantity squared, plus 1. And my y, I'm going to integrate with respect to y and then with respect to x. So the bounds for y are 0 and negative 13 over 2x plus 13. Squeeze that in there. And the bounds for the x integral are 0 to 2. So let's bring this down. We have 0 to negative 13 over 2x plus 13. And here we have 169 plus 4 plus 1 makes 174. And we're going to integrate with respect to y and then with respect to x. So when we integrate with respect to y, we just put a y on it because it's a constant. So we're going to say the square root of 174 times y from 0 to negative 13 over 2x plus 13. And we have a dx at the end. So the integral from 0 to 2, the square root of 174, parentheses, negative 13 over 2x plus 13 minus 0 with respect to x. Now I'm going to pull the square root of 174 out. So we just have a pretty binomial here so we can integrate. So we're going to say the square root of 174. When we integrate negative 13 over 2, we get an x squared and a 1/2. So we have negative 13 over 4x to the second plus 13x from 0 to 2. So we have the square root of 174. Now 2 squared is 4, so that cancels to be negative 13 plus 26 minus 2. So we end up with 13 square root of 174. This is the surface area of the region that they asked us to find. So if you look at the problem in your homework, this is question number 3 in your homework. And it says first of all, now that we've done the whole problem, let's go back and talk about what WebAssign is looking for. The first thing it asks is find the area of the region D in the xy plane that lies below the surface. So if we go back up to our triangle up here, this is our region D. And if we find the area of D, this is not hard because it's a triangle. So the area is 1/2 base times height, which is 1/2 times 13 times 2, which is 13. Now there's a second way to look at this. If we were to go right here, let's look at this notation right here. And we say the double integral of the area, the square root of 174 dA. If you pull this square root of 174 out, we can say the double integral over the region and the area. Well, when we did this part of it, that's what we did all in the blue down here, and we got 13. So we got the square root of 174 times 13. So this is our area of the region and the xy plane, the 13. It's what we got for the integral there. So the answer here, no matter how you want to look at it, is 13. And then part B actually says find the area of the surface, and we find that to be 13 times the square root of 174. Now they do have you pause and put the 174 into the double integral up there without bounds, but I'm sure you can handle that. All right, let's look at another one. This problem says find the area of the part of the paraboloid z squared equals x squared plus y squared that lies under the plane z equals 9. So let's start off with f of xy is equal to z, which is x squared plus y squared. Now in order to come up with our bounds, we need to take x squared plus y squared and map it to the xy plane. So that 9 helps us out in that area. We have a circle with the center at 0, 0 and a radius of 3. Now keep in mind that x squared plus y squared equals r squared. So since r squared equals x squared plus y squared, that was going to help us out greatly. That's why we need to know these things so we can pull them in when we need them. I'm not going to go into bounds yet because I can see the future and we're going to need to work in polar. So let's hold off on bounds conversation for just a second. And our partial with respect to x is 2x, and our partial derivative with respect to y is 2y. Now we can look at the area of the surface and say we have the double integral over the region D of the square root of the partial with respect to x is 2x squared, plus the partial with respect to y is 2y quantity squared, plus 1, and we're going to say integrated with respect to the area. So the double integral over the region, and here we have 4x squared plus 4y squared plus 1 with respect to the area of the region. Now when you get here, you cannot integrate this with respect to x or with respect to y. U sub is not going to work, and you have multivariables, so there's a lot going on here. Your best option here is to turn this into polar. So let's go one more step before we turn it into polar and say we have the square root of 4 parentheses x squared plus y squared. See how that's going to be our r with respect to a. Now we know here that r equals x squared plus y squared, so that's not going to be bad. But remember that when we switch to polar, we don't just put xy, we're going to put r dr d theta. So let's go back over here, and this becomes 4r squared plus 1, and we have r dr d theta, and then we have to think about bounds. You can see that when we take this shape and put it on the xy plane, the circle is a solid circle. It's not just an outline of a circle. So our bounds for r are going to be 0 to 3. So now we're going to integrate this with respect to r. I'm going to rewrite it and put my r a little bit better and a little bit closer so it doesn't feel like it's hanging out way on the end. So we have 0 to 2 pi for our bounds for theta, and then 0 to 3. And I'm going to put my r here, and we have the square root of 4r squared plus 1 dr d theta. Now, let's integrate with respect to r. We need to use u sub. So let's let u equal 4r squared plus 1. And so du is equal to 8r dr. So dr is equal to 1 over 8r du. And let's plug this in. So we have 0 to 2 pi. And then I'm going to leave my bounds off because I'm changing to u. So I have r times the square root of u. And then we have times 1 over 8r du and d theta. Now when r equals 0, u is going to equal 1. And when r equals 3, u is going to equal 9 times 4 is 36 plus 1 is 37. So we can put these bounds in, 1 to 37. So we're going to bring this down, the integral from 0 to 2 pi, and the r's are going to cancel. We have the integral from 1 to 37, and we have 1 over 8 times u to the 1/2, integrate with respect to u, and then with respect to theta. I'm going to come back to this line in a few minutes, but I'm going to leave it here for now. So we have 0 to 2 pi. And we have, when we integrate with respect to u, we get 1/8 times 2/3 u to the 3/2. It's that beautiful 3/2 we can't get away from today, from 1 to 37. And so the integral from 0 to 2 pi, this gives me 1/12 times 37 to the 3/2 minus 1 to the 3/2, which is 1 d theta. Now I'm not going to worry about making that pretty because it's all a constant. There's no variable there. There's no theta. So we're going to integrate with respect to theta and say 1/12 times 37 to the 3/2 minus 1 times theta from 0 to 2 pi. So this means we have 1/12 times 37 to the 3/2 minus 1 times 2 pi minus 0, which is 2 pi. So we have 1/12 times 37 to the 3/2 minus 1 times 2 pi. Well, that gives me 1/12 of 2 pi is pi over 6. So let's say pi over 6 times 37 square root of 37 minus 1. Now that's our answer, and we're going to stop and be happy with that. But I want to come back up here and show you an interesting technique. When we get here and we get ready to integrate, we can see down here that d theta, there are no d thetas. D theta does not affect dr in any way. If you are unsure of this, I would never do this, but we could say the integral from 0 to 2 pi of d theta times the integral from 1 to 37 of 1 over 8 u to the 1/2 du. We can multiply the integrals because there's not multivariables in them, so we can find the two integrals separately and multiply them at the end rather than integrating along the way. I'm not a big fan, but this would be 0 to 2 pi, and this would be 1/8 times 2/3 u to the 3/2 from 1 to 37. So we have 2 pi minus 0 times 1 over 12 parentheses 37 to the 3/2 minus 1 to the 3/2, which is 1. So you can see that that's the same as this line down here, and it'll take you into pi over 6 times 37 square root of 37 minus 1. It only works because there are not multiple variables happening there. So you can take the two integrals separately and multiply them. But if you're in doubt, don't do it, okay? All right, so find the area of the surface of the part of the hyperbolic paraboloid that lies between the two given cylinders. So let's start with our hyperbolic paraboloid. So f of xy equals z equals x squared minus y squared. And that's our surface. And look at the fact that our region is x squared plus y squared equals 9 and x squared plus y squared equals 16. So it's between those two values. So let's write it this way for our domain. By the way, when we do this, remember that we have a circle here with a radius of 3 and 4. So x squared plus y squared is r squared. So we can say that 9 is, the r squared is between these two. So r is between 3 and 4. So you can see it's heading into that polar direction, and life is very, very good here. So let's start with our partial with respect to x. By the way, when we do that, we're looking at the whole circle, so our d theta will be from 0 to 2 pi. So our partial with respect to x is 2x, and our partial with respect to y is 2y. So we're going to say the area of the surface is equal to the double integral over the region, and we have the square root of the quantity of 2x squared plus the quantity of 2y squared plus 1 with respect to the area. So we're going to say the integral over the region, and we have 4x squared plus 4y squared plus 1, and we're integrating with respect to the region. So now I'm going to go ahead and do a couple things here. I'm going to do my double integral, and I'm going to say 4, and I'm going to go ahead and say 4r squared plus 1. So that means we have r dr d theta, and r is from 3 to 4, and theta is from 0 to 2 pi. So let's keep this 0 to 2 pi, and when we integrate r, let's go ahead and say the integral from 3 to 4, and rewrite it to be r times the square root of 4r squared plus 1, dr d theta. It's a little easier to work with there. And we're going to use u sub. So let's let u equal, this feels very much like the last one, 4r squared plus 1, and du is 8r dr, so dr is 1 over 8r du. And when r equals 3, 3 squared is 9 times 4 is 36 plus 1 is 37. And when r equals 4, 4 to the third is 64 plus 1 is 65. It's going to be a messy answer. So we have the integral from 0 to 2 pi, the integral from 37 to 65, and that r is going to cancel, so we have 1/8 times the square root of u du d theta. So when we integrate with respect to u, we get 1/8 times 2/3 u to the 3/2 from 37 to 65. Very messy answer, d theta. So the integral from 0 to 2 pi, this is 1 over 12, 65 to the 3 halves, minus 37 to the 3 halves with respect to theta. So when we integrate this with respect to theta, we just get a theta. So we're going to say 1/12, 65 to the 3 halves, minus 37 to the 3 halves, times theta from 0 to 2 pi. So we have 1/12, 65 to the 3 halves, minus 37 to the 3 halves, and 2 pi minus 0 is just 2 pi. So we get pi over 6 times 65 square root of 65, minus 37 square root of 37. And that's our answer. Not too bad. I wanted you to see one that we did between the cylinders so that we could make sure that we were on the same one. Okay? And I think that's all that you need to be prepared for this lesson and be able to do your exercises. Hopefully you understand and have a great day.